In this video, I'm going to look at all the organic reaction mechanisms questions from the organic papers from 2017 and 2018. The link to the questions is in the description of the video, so if you wanted to have a go at them first, click on the link, download the questions, and then play on when you're ready for the answers. So just like I did with the organic synthesis video, I've just taken the parts of a question to do with this topic. So you can see this question here starts with part D. So the first part of the question suggests how an HBr molecule can act as an electrophile. So as a reminder there, an electrophile is an electron pair acceptor. So if you think about an HBr molecule, it's got a dipole across it, slightly positive on the hydrogen, slightly negative on the bromine due to the electronegativity difference. So this part, this slightly positive hydrogen, can accept a pair of electrons, and they obviously come from that pi bond in the double bond. Next part of the question, we've got to draw the structures of the two organic compounds formed from the reaction when HBr reacts with compound D. Basically, the HBr is going to add across this carbon-carbon double bond. So one of the compounds could be where the H goes on this carbon, the Br goes on there, and the other one would be the other way around. So the Br on there and the H on there. So I'll just draw those up now. So there they are there. Now all I would say here is just to be careful with what's called your connectivity. It comes up on examiners' reports quite a lot that students lose marks because they don't quite connect the atoms together properly, and it often happens in displayed formulae like this. So what I mean by that is, say this carbon here has got to be lined up, connected to that carbon there. So sometimes I would see, if I'm marking work, something like that, that would be marked wrong, believe it or not, because what that's implying is that the carbon is bonded to hydrogen. Okay, so moving on to the mechanism now, we can go for either compound E or F being formed. I'm going to do both because it's going to help with the last part of the question. So the first part of the mechanism, obviously this polar HBr molecule will accept a pair of electrons from the pi bond. So we draw a curly arrow from the pi bond to the slightly positive H. And what that's going to do is it's going to repel the electron pair completely onto the bromine and break that bond by heterolytic fission. So just be careful. This curly arrow's got to start from the bond, and this curly arrow's got to start from the middle of the bond. Okay, so there's my two carbocations. So to finish the mechanism off, I just need to take a curly arrow from this lone pair on the Br minus ion onto that positively charged carbon, likewise for this one. So I'll just draw the products up now. So there they are there, but remember the question did say either, so you could have just gone that way or that way. Okay, so I'm just going to call this one here E and this one here F. It doesn't matter which way around you do them. It's just going to help us answer the last part of the question, which we'll look at now. So which of E or F is the major organic product? So the answer to that lies in the type of carbocation we've got. So this carbocation here, so if we look at the carbon that's got the positive charge on, how many carbons is directly bonded to that, or how many carbon groups is directly bonded to it? 1, 2. So this is a secondary carbocation. This one is the C plus has got 1, 2, 3. So this is a tertiary carbocation. So the major product, the way I've labelled them, is going to be F. And that's because it's being formed from a more stable tertiary carbocation. The secondary carbocation isn't as stable, and so therefore not as much of E will be formed in the reaction mixture. Next question, pretty straightforward, it's just the mechanism for the nitration of benzoic acid, but just bear in mind we've got to produce the 3-nitro product. So the first step of the mechanism is the formation of the electrophile. So that's when your nitric acid and your sulfuric acid react together to form the electrophile. So that's the NO2 plus ion, nitronium ion. You get an HSO4 minus ion, and you get a water molecule. Next part of the mechanism, the electrophile reacts with the benzene ring, so a pair of electrons from the pi electron cloud comes out to the electrophile. Just make sure you start that at the circle, and we draw up the intermediate, which looks like that. Just remember that this partial electron cloud, I always tell my students to cover 5 carbons, 1, 2, 3, 4, 5, and it's got to be open where the substitution's taking place. Don't forget your positive charge as well. And then this stabilizes itself by a pair of electrons going from that CH bond, so go from the middle of the bond, curly arrow, back in to reform this pi electron cloud. So there's the product there. Don't forget your H plus ion, that's what this will come off as. And then we just need to show how the sulfuric acid behaves as a catalyst. So you take your HSO4 minus ion formed in the first step, H plus ion, it's just been kicked off that benzene ring, and you get your H2SO4 back, so it's a catalyst because it's reformed. Next question, outline the mechanism for the reaction between 1-chloropropane and ethanolic sodium cyanide. So we need the Cn minus ion, that's going to act as a nucleophile in this reaction. The dipole across that CCl bond, delta plus on the carbon, delta minus on the chlorine. So a pair of electrons is donated to that C delta plus, that's why it's a nucleophile, electron pair donor, and this CCl bond breaks by heterolytic fission and it generates the product. Okay, so there's the products there. So we've got this nitrile being formed, this would be butane nitrile, and we get a chloride ion as well. Next question is slightly tricky, I suppose, because it's not straight off the syllabus. It's an application of one of the benzene mechanisms. So we've basically got to see how this methyl benzene is going to interact with this electrophile here, and we have got the products, so that's obviously a big help. So if we have a look at what's changed, obviously the sulfur has bonded to this carbon, and this double bond's broken, and it's become a single bond, and there's a negative charge on that oxygen. So to make that happen, what's obviously gone on here is a pair of electrons is gone from the pi electron cloud to that slightly positive sulfur, and that's repelled the pi electron pair onto that oxygen at the bottom there. So the intermediate's going to look like this. So just remember that rule of 5 carbons with your partial electron cloud, open where the substitution is. Don't forget your positive charge. And obviously to get that H plus, a pair of electrons is going to go back into reform that delocalized ring of pi electrons, and that'll come off as an H plus. So we show that with that curly arrow like that. So moving on to the next question about the hydrolysis of the haloalkanes. You can see I've already written up there the trend in bond strength. So we've got decrease in bond strength going down group 7. So the strongest carbon halogen bond is the CF bond, weakest is the CI bond. So basically a fluoroalkane will be hydrolyzed the slowest because this bond's too strong. This iodoalkane would be hydrolyzed the fastest because this bond breaks really easily. So in terms of an answer, something like this. So the rate of hydrolysis is linked to the strength of that carbon halogen bond, and then the trend, the carbon halogen bond strength decreases down the group, and then just a couple of examples. I've just gone for the extremes. Fluoroalkanes are hydrolyzed the slowest, iodoalkanes are hydrolyzed the fastest. And part B is just a mechanism for the hydrolysis of chlorocyclohexane with aqueous sodium hydroxide. So we're only interested in the hydroxide ion from the NaOH. So relevant dipole would be across this carbon halogen bond, and a pair of electrons would be attracted to that slightly positive carbon, and that's going to break that carbon halogen bond by heterolytic fission. So in terms of products, we just get a straightforward substitution of the chlorine for an OH group. So we get this alcohol formed, and obviously the chlorine's going to come off as a Cl minus ion. Okay, so moving on to the last question, the mechanism we've got to draw for the formation of one of the organic products when methyl cinnamaldehyde reacts with ICl. So you can see I've already drawn up an ICl molecule, and I've put the electronegativity values in to show which way around the dipole is going to be. So the iodine is slightly positive with its lower electronegativity value, and the chlorine is slightly negative. So like before, I'm going to show the formation of both of the organic products, and that's going to help me explain this part of the question, explain which of the two possible products is most likely to be formed. Okay, so cinnamaldehyde, it says you can use C6H5 to represent the phenyl group, so I've done that. So first part of the mechanism, pair of electrons from the double bond will be attracted to that slightly positive iodine, and that'll break that ICl bond by heterolytic fission. So I'll draw both of the intermediates up here. Okay, so there's the two intermediates there. So all we need to do is take a curly arrow from the pair of electrons on the chloride ion, and that's going to form the product. So the final bit, we've got to explain which of the two products is most likely to form. So it's all linked to the type of carbocation in the intermediate. So if we look at this carbocation here, so we're focusing on this carbon with the positive charge on, that's bonded to two carbon groups directly. So this is a secondary carbocation. Whereas this one here, you can see we've got 1, 2, 3 carbon groups. So that's a tertiary carbocation. So this product's the most likely to form, and that's because it's made from that more stable tertiary carbocation.